You ever wonder how trees manage to get water from their roots to the very tops without a pump? The secret is in osmotic pressure. Let's explore. Let's think about a giant sequoia like you might find in California. On a summer's day, it might have to shift over 500 gallons of water to over 300 feet. This isn't a small job. The solution actually lies in using osmotic pressure with a little help from capillary action, but you can go through that in biology class. First things first, what is osmotic pressure? Osmotic pressure is the pressure exerted by a solvent to prevent the inward flow of water across a semi-permeable membrane. It also depends on the molarity of the solution and the temperature. To calculate osmotic pressure, we use the formula pi is equal to mRT, where pi is the osmotic pressure, m is the molarity of the solution, r is the ideal gas constant, and T is the temperature in Kelvin. Now let's look at an example. The osmotic pressure in the roots of large trees can actually reach 19 atmosphere. What molarity of a tree sap solution would cause this pressure on a day when the root temperature is 15 degrees Celsius? Well, first, we need to rearrange our initial formula to make molarity m the subject. Now let's substitute in our values. The osmotic pressure pi is 19. R, the ideal gas constant, is 0.082. To convert the temperature from degrees Celsius to Kelvin, we add 273 to it, meaning that T in our formula is 288 Kelvin. Using these numbers, we get a final value of 0.80 molar. This tells us that in order to have an osmotic pressure of 19 atmospheres on a day with a root temperature of 15 degrees Celsius, the molarity of the tree sap needs to be around 0.80 molar. Knowing how to use osmotic pressure to calculate the molarity of a solution is useful elsewhere too. It gives us an alternative method as chemists with which to accurately determine the molarity of a solution. A quantity that is important as it allows us to control and predict the outcomes of reactions. And finally, what does this mean for trees? Well, if we look at the equation, it tells us that the greater the molarity of the tree sap, the higher the osmotic pressure in the tree, and hence, the greater movement of water up that tree. It also tells us that during the warmer months, the osmotic pressure in the trees will be higher. This makes sense, as during these months, they will be photosynthesizing more and thus have a greater need for water in their leaves. So now you know, no pump required on a tree, just a clever use of osmotic pressure. That's pretty neat, huh?